you guys can go back to the others. So, other questions? Hello, hello. Anyone there?
I'd say just like chapter 14 in general is pretty hard for me, at least. This is
It's a lot of stuff.
yeah, no, I know. I'm sorry. It's just like I don't know. A lot of it's confusing for me.
Chapter 14. So let's think of some of the most common parts. When you're, let me try to think of what's the best way to work through that. When we're thinking of rate laws, right, you're trying to find the right slide. Let me see. Can't find the slide I'm looking for. My computer is going very slow right now for some reason. Come on. Let me share this. Hey, Elizabeth.
Hi.
So you joined us.
Yes.
We've just covered one problem. I'm just a little having some technical issues here. All right. All right. So when we're talking about rates, we have find the reaction. Where's the reaction? Right here. So if we look at this reaction up above, color coding, do I have on right now? I have red. All right. So we have our reaction up above, right? Drawn up above here. And we have the C4H9Cl plus water reacting to give us our C4H9 alcohol OH plus hydrochloric acid. And when you're thinking of rates, right, you can have rate equal to each of the individual reactants and or products. When you're talking about rates that are for disappearance, I'm just going to kind of give you an overview. Right? A disappearance, right? We're going to see the disappearance of this reactant. So we see a negative change because you never want to have a rate equal to a negative numbers because things don't go in the reverse direction. When you have things going the forward, being formed like the product here, you have the rate is going to be positive. And obviously for this particular equation, the speed at which the reactant is being consumed is going to be equal to the speed at which the product is being formed. So when you're thinking rates, realize that that's what's going on here. We also have, right, there's HCl. I mean, we left it off, but you could just as easily have added, right, this is equal to the change in the concentration of HCl over the change in time as well, right? So you could just as easily put all of those in. So that's what we're talking about with overall rates. that's one part of what we discuss, right? And then if you have differing ratios, like you have here, then your rate is going to be 1 over whatever that number is. So this 2 comes down to here, right? And the 3 comes down to here. And if you think about how that makes sense, if we think about it from a mole-to-mole ratio, right? If we wanted to understand just the concentration, this part right here, right? So let's just say we were going to solve for the change in concentration of ozone divided by the change in time, right? So that's going to be equal to, you can see that would be equal to, well, let's leave that negative for now. It's equal to 2/3 times the change in concentration of oxygen over the change in time, right? And this 2/3, let me change the color. Right, this 2/3 that is sitting here, think about the original equation, go back to last semester, we know that we have for every 2 moles of ozone, we're going to produce 3 moles of oxygen, right? So we know that we can create an equation which states that, you know, our conversion factor we can have as 2 moles of ozone divided by 3 moles of oxygen, right? So you can see this 2/3 is just the ratio that is there for converting over from ozone into oxygen, right? You know, this is going to, if you can very easily convert between one unit and the other. All right. Skip ahead. So in this section, so the first part that we were talking about back here is just taking into account individual concentrations of reactants and products and relating that, you know, it's a change in concentration component divided by a change in time component. Okay. So whereas we can look at rates in a different way, where instead we can have our what am I looking for here? Give me a second. Right. So instead, we can look at rates where we have a constant times the concentrations of the individual reactants, and you can see how, you know, this would be, you know, this is going to be equal to, right, just the change in concentration of NH4. Stupid thing. Plus over the change in time. Right, so you can see how now you can relate some rate constant to a individual substance, because if you know an exact amount of time that it's reacting. So this allows you to switch, you know, it gives you the ability to measure individual reactants, right? It's very easy. Well, it's very easy to, occasionally easy, when you have things that are UV absorbent, like we did in lab. We can measure a concentration change, and you can use a stopwatch, and with that stopwatch measure a change in time. And then you can relate that back to, you know, based on, you know, what you know for the concentrations of the reactants. You can then solve and figure out what your rate constant is. So it's a way of working back and forth between the two. Does that help clear anything up for you? Dominic, you there? Dominic? Did I lose you? Okay. All right. Anything else you want clarified in chapter 14? Because that was a broad question. I was just trying to speak generically about it. There's a lot more in the chapter. Anybody else have any other questions?
So could we go over, this is chapter 15, but the difference between like Q and KP, or just how you use them to figure out which way the equilibrium shifts?
Sure.
Okay. Thanks.
Mm-hmm. Right. Let's see. Right there. All right. All right. So when we're talking about equilibria, there's really the difference between Q and K. You calculate them the exact same way. So that's the first thing you need to understand is Q and K are the exact same equation. There's no difference between the equations. The only purpose of calculating Q is just to understand which direction the equilibrium is going to shift once you have some effect. I'm trying to. This is not going full screen for some reason. All right, here we go. So let me see here. So when you're going through and you have an equilibrium, let me just find, let's just say here we have an equilibrium constant here. All right, so I'm going to take and transpose this one on slide here, right? Well, let me just write right on here. Right, so this when we have an equation such as this at equilibrium, and you can see we end up with a specific equilibrium constant, 51. Right. So if we were to then instead, use the exact same equation, but now instead of 1.87 times 10 to the minus 3 squared for concentration, let's just say, I don't know, let me think of, calculator, make the math easy. .35 times 10 to the minus 4, right? So let's just say, actually that's a product. Oh, that's fine. Let's just say we measure the reaction and we had 9.35 times 10 to the minus 4. And just for the ease of writing, just assume the denominator is exactly the same. All right, so all I did was divide the concentration, right? This is the difference between these two is just dividing by 2. So our reaction quotient after we do the math out in the end is going to be, right, 25.5. And what that tells us is, you think about what this equation is telling us. So if we have 25.5, I'm going to go down, right? If our reaction quotient is smaller, right, than the equilibrium constant here, then the reaction wants to move forward to form products. The reaction is going to be driven forward. You want to go towards the forward direction. And if we go back to this equation, the picture up here, think about it. We have 2 times less reactant. We have 2 times less product. There's less product in this particular reaction. So since there's less product in this reaction, in order to balance, you need to form more product, right? You need to essentially in order for the reaction to be happy, so to speak, we need to have more product. So this area up here has to look like that there. So we need to increase heading towards 1.87 times 10 to the minus 3 in order to try to bring that 25.5 up to 51. So whenever you have it, when you think of the easiest way that I want you to think of this is when you're looking at and comparing these numbers, you have 25.5, and you're going to need to multiply it by some number, either I'll call it. Let me clean this up a little bit. Right, you have change the color. All right, so we have 25.5, and we're going to need to multiply it by some number. We'll call it x over y in order to make it equal to 51, right? So you can see here in this particular example, I would have to multiply this by 2 over 1, right? So what this is telling you is since we have to multiply by 2 over 1, that we want to head towards making more product, right? Because we have a larger number on the top, right? The numerator is related to the product, because our equilibrium constant is always products over reactants. So that's why when we see it, whenever we have an equilibrium quotient Q that's smaller than the equilibrium constant, we're going to be driven towards products. Whereas conversely, if Q is greater than K, then we're going to go in the opposite direction, right? Because now, if we had instead for some reason, let's say 102, right? If the answer was if Q was equal to 102. Then you'd have 102 times x over y is equal to 51. So obviously this would have to be a half, right? So that means you'd have to increase your denominator, which are your reactants in this case, in order to drive the reaction towards completion. Does that answer your question?
Yeah, it does. Thanks.
Yep. Other questions?
Can you do one that's like the rate of like appearance and disappearance?
Rate of appearance and disappearance. Do you have a particular problem in mind? Which chapter are you talking about? You're talking about
Yeah, chapter 14.
14. Rate of appearance and disappearance. Let's see. Let's see.
Like I was gonna say, number 1 on the problem set of chapter 14, I don't understand.
Okay. Easy enough. Be sure of that right now. All right. All right, so here we go. And problem number 1, I remember this problem. This one was designed to challenge you. All right. So it's asking you, it says, consider the following hypothetical aqueous reaction of A going to B. A flask is charged. Charging just means filling with a quantity of A in a total volume of 100 milliliters. And the following data are collected, right? So we have, you can see for what we're measuring here is the rate of formation of product, right? We're increasing the amount of product, so that's what we're seeing over time. We're not seeing disappearance. But then question A then says, calculate the number of moles of A at each time in the table, assuming that there are 0.031 moles of A remaining at time 40 minutes, and that A cleanly converts to B with no intermediates. So all I did in the first part and the answer key here is I just took this portion here is literally just the table up above, right? So that's just this transposed sideways, just to make it easier. You could have easily kept it left to right. Now, what I told you in the problem was that it's at time 40 seconds, or 40 minutes, I'm sorry. 40 minutes, you have 0.031. So that tells you that when you add A and B, right, we know we're going to have the total must always equal 0.065. Right? Because there's the total number of moles in the system has to equal 0.065 all the way across the board. And the reason for that is because we know that when we go from A to B, we have 1 mole of A goes over to 1 mole of B. So you can see that all that's done for the steps above is we just take 0.065 and here, and we're going to subtract from that, all of these numbers, right? I'm going to place those numbers into that spot, and you calculate all the moles of A. With me up to there? And that.
You know that.
I was just going to say that makes sense.
Okay. So now, what we do know is in order to calculate concentration of B, we're told that we have 100 milliliters of solution, and all concentration is moles divided by volume, right? Moles divided by volume. So all we do is plug in the number of moles, right, of B. So we take column B, and we plug the moles in up above and solve for the concentration of B. So all we're doing is simply solving, right? 0 divided by 0.1 is equal to 0, right? 0.014 divided by the 0.1 up there gives us the 0.14, right? 0.23. All you're doing is basically moving the decimal over by one place because you're dividing by 0.1. So you get your concentrations of B. Now we know the change in concentration, all we have to do is subtract, right? So we take the 0.34, right? 0.34, we subtract 0.29, and that gives us the 0.05, right? The 0.29 subtract the 0.23, and you can see we end up with the 0.06, and then keep going down the line, right? And then 0.23 subtract the 0.14, we end up with the 0.090, etc., all the way down. So those are our changes in B. So we know what the change in concentration is, right? So that's basically, we're looking at not moles, but we've converted, in order to calculate rate, we don't need moles, right? We need concentrations. So what we've done is basically converted these mole numbers over into concentration units. Now that we have concentration, we can then just do the calculation. We know that in between every single step, as we calculated before, right, we have a change in 10 seconds in between every single step, right? 10 seconds, 10 seconds. There's 10 seconds between every single step. So all we're going to do is simply start, you're going to plug that in, right? Or we take our, not 10 seconds, 10 minutes. So we take all of these B's and we're going to plug them in the equation up there. We're going to divide by 10 minutes for each of these. We know rates are in seconds, so we need to convert over from minutes to seconds. So the minutes will cancel, and then we do the math, right? And that's what's being done down here, is we simply plug in. So in the bottom case, let me see if I can change colors here. I can't. Oh man, I just messed up here. Give me a second. All right. So you can see that basically all we did was, for the for 8.3 times 10 to the minus fifth, all we did was take the 0.050, divide it by 10 minutes, and then divide it again by 60 seconds, and that's where this rate came up with. We just do that for all of the concentrations, and we get all of our rates. So that allows us to then basically determine the rate at each time, over each range, right, over a certain time period. All right. And all this question is asking you to do is basically look and do the exact same thing, just pulling the data instead at time equals 30. Wish I could change the pen color easy. But time equals 30 and time equals 10, right? So we're just basically looking at the change in concentration over the change in rate, starting from those 2 points and plugging those in, because we now have our concentrations. Do you need any more clarification?
No, I think that's good.
There's a lot of scribbles there, but anyone else?
Just one more clarification. How do you know if it's first order or like second order again?
First order, second order reactions. When we do that you need to, in order to calculate first order versus second order, you would need more data, like in problem number 2. So like in this problem here, right? So in this problem here, we're given concentrations. So you're given concentrations and rates. So we need concentration and rates in order to do that. And you can see what we're doing is, in one case, the first 2 cases, we're holding the concentration of I minus the same, and we're changing the concentration of CH3Cl. And all we're going to do is we have our rate equation, right? So if we look at the reaction up above, we can see that our rate, right? The rate of this equation is just equal to the K times the concentration of CH3Cl times the concentration of I minus. Oops, no, minus. Oh well, it's not allowing me to erase right at the moment. There's a minus. All right, so what we're going to do is, since we're holding the concentration of I minus the same, so if we do look at the problem down below. What the goal is to take, and we're just simply going to compare these reactions to each other. And one of the things that the textbook doesn't do very well, and I probably didn't put it in here very well, is what you're trying to do is you're trying to, on the right hand side here, it's really trying to figure out what the exponent, I'll call it x for now, for lack of a better term, what this exponent is for each comparison. So all you're simply going to do here is in the first step, we take our rate 1, right, our 1.36 times 10 to the minus 9th for the first rate, and we can see that we know that that rate is equal to k times the 1.5 times 10 to the minus 3 times the 1.5 times 10 to the minus 3. All I did was take all of this data from the very first line, and I put all that into the rate equation up there, right? And then I have the exact same thing for line 2, right? Line 2, I have our initial rate here, right? The initial rate. And then I have the K times those concentrations for that second line. And I'm going to compare them. So when I do this, right, when I take 1.36 times 10 to the minus 9th and I divide the two, I end up with a ratio of 0.5, right? So that's 0.5. Then when I do the, on the other side, you can see that these 1.5s cancel. They cancel each other out. The K's cancel each other out. So I'm left with the 1.5 times 10 to the minus 3 over 3.0 times 10 to the minus 3, which is 0.5. And if I bring this x back in here, so if I put x on the outside, then we know that this exponent x has to be equal to 1, right? And this x equal to 1 tells us that because the only thing that was changed was the CHCl3, that when we're creating our equation, this is going to be first order. So the rate equation that we're trying to figure out, I'll call that, if I go back up to the equation up at the top that I drew up on the board, that x there is going to be equal to 1. All right, so then you do the exact same thing now for lines 2 and line 3, because in line 2 and line 3, line 1 and line 3, not line 2 and line 1 and line 3, because now in line 1 and line 3, we're holding the concentration of the CHCl3 the same, and we're changing the concentration of the I minus. So you do the exact same thing for that. And in this particular example, you end up with again, 0.5 over 0.5 to we'll call that y. And that y, we're going to plug in to our rate equation. So we know that I is also first order because y is equal to 1 as well. So we know our overall rate equation that I've got written over here is just rate is equal to k times the CH3Cl to the first power and I minus to the first power. Did that answer your question?
Yes, yeah, thank you.
Anyone else? No one else? Sophia's here. Hi, Sophia.
Hi. So we're officially going to online classes for the rest of the semester?
The rest of the semester. You got the message. I just read the message about 10 minutes ago, or 10 minutes before we started. So.
Wow. That is crazy.
It is. We're living in a crazy time right now.
So will the exam be just like the practice one?
What do you mean, like the practice? The practice one was just to get you used to the types of problems, but that
Okay.
those were actually just all I did was copy and paste sample problems into the exam.
Oh, okay.
It wasn't meant to be anything more than, just get you used to using the software.
Yep.
Yeah, those were sample problems. So yes, it should look like those though, but it's not, obviously going to be a little longer.
Okay.
Any other questions? No other questions? Everybody knows everything, or nobody studied yet because half of you decided to take it on Saturday.
So are we allowed the whole day Saturday to take it?
Well, anytime during the day, right? So I'll
Okay.
probably have it like from 8 to 5 or something, just like I did on Thursday.
Okay. I won't be able to take it during 8 to 5.
You won't.
I won't.
Send me an email with your proposition.
Okay.
Any other questions? Is everybody ready for the exam? Everybody's tested out the software hopefully by now. Make sure it's working. Nobody's having any troubles, no issues.
So I had a question when it comes to like recording your surroundings.
Yep.
Is that just like recording every single angle like all around you?
Yeah, that's the goal. It
Okay.
just, kind of do a 360 all the way around and then look up, look down.
Okay.
Just to make sure you don't have any gremlins hiding under your desk giving you answers. Or to make sure you don't have any where's Brian? Brian disappeared. He was on a little while ago. Now he's gone. Oh well. Brian was funny. He's running the practice and he had some his roommates or somebody there. And they're like, "Oh, Dr. Barboza will probably see this." And that was just happened to be the halfway point when I paused to see what, he happened to be the first one I looked at. So we get to watch you, so make sure you look dignified. Any other questions? No other questions. Everybody's got this. I have a feeling we might need to do another one of these on Friday night for the many lost souls traveling today. There are a lot of students that are traveling today. So. Going once. If nobody has any questions, I'm going to go eat dinner. Going twice. Stay safe, everybody. I know it's kind of crazy times right now we're going through. Don't go spending a lot of time out in public. No matter how tempted you might be, I would suggest against it unless you plan on not seeing your older adult family members, grandparents, maybe even some parents, because you're likely to bring it home. I was just told that there's apparently some student who has pneumonia on campus that a professor ran into, who was, because they're not checking him for coronavirus, or him or her, I don't even actually know if it's a he or she, because of the fact that they don't have a fever, but they do have pneumonia. So, and apparently what they're testing for right now, you need pneumonia and a fever. So be aware. The reason they're going into these quarantines is because people are out there. Likely that person is going to survive and will be perfectly fine because pneumonia doesn't usually kill young people. But I would hope that person wouldn't go home to mom and dad. Alrighty. Any more questions? If not, then I will see most of you I guess I'll speak most of you on Friday again. Alrighty. See you later. Bye, everyone. I'm going to turn off the recording. So this recording will be here